Nice.
Okay.
Okay, welcome on Meetup. Alexander, stage is yours, so go on.
Thank you. Thanks for having me. Glad to be here. Um, yeah, so I guess timekeeping, we're gonna spend about 20 minutes doing the slides, and then I want to leave some room for questions. There'll be a demo at the end, just so that everyone knows what's coming. I think that I will talk a lot about co-designing a new storage engine using a thread code architecture. And the code is available on GitHub, is under the BSL license. It means in 4 years, it becomes permissively licensed. So it's Apache 2 and 4 years. For the first 4 years, anyone can use it. Nobody has to pay us unless they use an enterprise feature. And yeah, that's basically it, unless you want to compete against our SaaS, right? We have like a vectorized cloud. But other than that, you could use it for your project as a drop-in replacement. That's what we'll talk about today. So a little bit about me. I wrote actually the first pass of the storage the storage engine with kernel bypass. Prior to that, I was the principal engineer at Akamai, and I was also a CTO of Concord, which was basically a computational engine, also in C++ that I sold to Akamai in 2016. Think of it like Spark streaming, but in C++. I know recently Databricks rewrote their Spark in C++, so I think we were right, probably just 6 years too early. Let's see. So today, I think I want to talk a little bit about, this is some repurposed slide from HydroConf that I put together yesterday. Fundamentally, CPUs, the new bottleneck, is what I'll talk about today, and why you need a new way to build software to leverage modern hardware, in particular NVMe SSD devices, to get 10 to 100x better tail latencies. So I think the gist of the talk and the implementation of Redpanda could really be summarized as that sometimes you get to reinvent the wheel when the road changes. And so the analogy that one of our advisors likes to say, excuse me, the analogy that one of our advisors likes to say is that, like, you know, first wheels, when you have horses and carriages, there was like wooden innards of the wheel, and then you had this metal thing, and then asphalt or road came about, and you had to reinvent it and come up with rubber wheels and so on. And like, there's actually quite a lot of innovation there. So the reason for that, though, is fundamentally on three parts of the computers. So let's see, yeah. The first one for a storage engine, like, remember that Redpanda is a storage engine. It's a linearizable engine, so in terms of data semantics. And we just added transactions last week. So it's a transactional storage engine. We added a Kafka API. And so it's actually not meant, I think people often tend to think about it as a replacement. And it is true that it is a replacement in terms of an API guarantee. But the design is fundamentally different in just about every meaningful way. And the reason where that design comes from is on three important things. And so software doesn't run on category theory, it runs on real computers. And what does that mean? And so it means that from a decade ago, you have, you know, computers are now, NVMe SSD devices in particular are 3 orders of magnitude faster, an order of magnitude cheaper. So you started at $2,500 per terabyte, and now you can get it on Amazon at $200 per terabyte. And if you look about the latency, if you actually go and look at the Linux kernel code, the IO subsystem was really optimized for the spinning disk tick, right? And so the idea is that you save a disk, and so the IO block subsystem will reorder your IO CVs such that you minimize basically the latency to copy the pages onto the spinning bus. And so basically it comes around, and you sort of have to figure out how to align it so that you get good throughput and low latency on that. So fast forward a decade later, saving a single page, and so the latency is just to give people like real semantics in terms of latency. Over a decade ago, it was in the single to double digit milliseconds to save a page to disk. Now on an NVMe SSD device, right, you're talking about single digit microseconds to double digit microseconds to save a single page to disk. The second material improvement as to why we invent Redpanda, like, you know, why did you start, is that the second material improvement on computers really comes from the increased core count. And so Herb Sutter, who's part of the C++ standard committee, wrote a famous paper a long time ago, I think, whatever, maybe 20 years ago. There's no free lunch. And what it really means is that you hit the frequency wall of CPUs, and now you're increasing core count, but it's real now. A decade ago, sure, you get four CPUs on Amazon, etc. But now you're renting 96 core VMs, 225 core VMs. So the real multi-core paradigm is here today. I think the multi-socket CPUs didn't become popular. Instead, the multi-core with a single socket became popular. And then the last one is the NICs that you actually are able to rent on AWS are basically 100x more throughput than you used to get over a decade ago. And so that's what we mean when sometimes you get to reinvent the wheel when the road changes. And so I'll explain why the CPU is the new bottleneck. And so if you assume, basically file open, then you file write and file close, f data sync and file close. Let's talk about what that is in terms of wasted CPU utilization. And so on the right, you have a network device. I think people look at this and they're like, oh, this is an NVMe SSD device. But if you actually understand how the message passing works in the kernel and the hardware, it's really a network device. And so let's say that you are, and this is, by the way, at NVMe SSD speeds, right? So let's say you're on a relatively non-contended, but some average utilization of this NVMe SSD device, you get 20 to 100 microseconds to save a single page to disk, right? And so if you are blocking, if you just say f write, and then printf, let's say at the next example, and you block on that syscall, you're basically throwing away 60 to 420 million clock cycles. And so the idea is that could you design on a new architecture where you actually leverage the way hardware is designed, right? So as opposed to hiding the complexity with the POSIX API, could you use some of the lower level APIs and actually map to the way hardware is designed and implemented? And so we use a thread per core framework called C-star. It's a small features library, kind of as the core of the execution model for Redpanda. But at the end of it, you can think of an n squared number of queues. And so what it is every core has an outgoing queue for every other core, right? So that's the model. And you communicate with message passing. And so as opposed to sending a global barrier for synchronization, what you say is you send the message to a particular single producer, single consumer queue, and you say, hey, core 32, there'll be a message waiting for you. And at some point in the future, on core 32's future execution time, it'll pick up the message and it'll do something. And what it means is that you're really building on asynchronicity first, trying to map to how the kernel and the underlying hardware works. And what it is that C-star is really an asynchronous framework, but it's a comparative scheduling framework. And so JavaScript is similar in that way, and many other frameworks. I don't know if maybe the first version of Go was also comparative. It means that you yield at functional boundaries. And so if you have a hot loop, you won't yield. So for I to a million, that doesn't yield. But you can yield if you inject a function call, right? And so if instead of that you use in C++, there's the coroutine implementation where C++20 code base, so super modern. It's really pushing the boundaries of the compiler. We tend to find a lot of compiler bugs for what it's worth. And so if in that hot loop you do co-return, right? So you tell the compiler to generate a state machine of the program and yield, then you get this comparative scheduling framework. And the two things to take away from this is, one is that future are viral primitives. So if people here have programmed in Akka, which is a lot of fun to program, or in C# with Orleans, or if you've written code in Pony, the language, or Erlang, really, is asynchronicity becomes always a viral primitive. But it's a really powerful paradigm for the developer in that you get to mix, map, reduce them, filter, change them, complete them, generate them, expire them, etc. And you're worried fundamentally about the program structure. And so you program to the concurrent structure, and you leave the simultaneity of execution to the runtime. So to the programmer, when you're writing code in C-star in particular, which is a very strict set of future primitive, there's exactly one thread per core. So if you have 32 cores on your computer. There are 32 simultaneous executions, full stop. There's no other thread pool. You can't add another thread pool because you'll stall the program. There are no locks on the head path. It is strictly about concurrency. It's a very strict mode of concurrency. It's different from other runtimes where they're like, yeah, you know, I use future too, and then I take a future and I schedule it on this thread pool. It's fundamentally different. What we're saying here is that there is a single thread per core, period, for everything that you have to do in that core, whether it's reaping IO from disk, or compressing, or encoding the Kafka format, or reading from the TCP network. And so it requires you to really redesign from the ground up the software. And so I'll share like 4 or 5 major fundamental techniques about the things that we do with Redpanda that are against common wisdom for what it's worth. And the gist is that we largely don't depend on the Linux kernel for a very large set of features. So the first one is we don't use virtual memory. And this is a relatively contentious thing. There's 2 things that are contentious. One, we don't use the file system page cache. We talk straight to the effectively the hardware. And then the second one is no virtual memory. And so the reason for that is that if you don't control the subsystem, then somebody else's problem is to control that subsystem, right? Like you can't eliminate the complexity of allocating memory. You can only push the complexity to somebody else. And so when we onboard the complexity of managing virtual memory ourselves, this is what the Linux kernel does, for example. Like the Linux kernel doesn't have virtual memory for itself. It is it. Like this is it for that. And so what we do is when we start up the program with Redpanda, we split the memory evenly across the number of cores. And every core in your head, it could operate as almost like an independent computer with low latency communication between cores. And so we use a body allocator mechanism. And what it forces the developer is it forces the developer to pay additional attention to things like hash maps and allocation and pooling and caches. What it gives us as the developer, as the programmer, in turn, what it gives you, the user, is effectively lower latencies in terms of jitter, right? So it's a very tight latency bound. There's no cross boundary to allocate memory. You don't have to go into the system for the system to give you a new pointer to a particular memory allocation. We sort of map it and manage it all in memory. And so it allows us to operate in user space objects like a Kafka batch, as opposed to operating in pages, where the Kafka batch may span multiple pages underneath. And so it's a very flexible model. It comes at the cost of obviously a lot of development time. Another one is, there are 2 major techniques I'll highlight. I'll send this presentation to you guys in case you wanna read it asynchronously as well. Is when you're dealing with no virtual memory, the fundamental problem is memory fragmentation. And so instead of like re-implementing the same structures of the Linux kernel, which is a generic scheduling mechanism, we actually implemented a new buffering layer. And so, you know, think of it in like, I think in Java it's kind of array map, in C++ it's totally different. It'd be like a vector of sorts. So actually there's a proposal called std colony, but without getting into data types specifics, it allows us to do memory deallocation across cores in a way that attaches to that n square number of cores, n square number of queues on a thread per core architecture. And so that was a lot of technical stuff. What it means is low latency allocation and deallocation. And so what we've built is a set of iterators over fragmented memory so that we don't have to always compact memory, right? Like at some point you do have to compact memory, but those things tend to introduce latency. I wrote a long blog post on that, so feel free to hit me up on Twitter if you have questions on it. There are a few techniques of why we're fast, and I'm about to jump into the demo in a few things. I just want to highlight a couple of things here. This is a much more technical talk that we have time for. But there are another major technique is because we speak directly to the hardware. We get to do things like using the sparse file system support. So as opposed to saving pages 1, 2, 3, 4, imagine you have two sectors of your NVMe SSD device, and the first 3 pages fit in sector 1, but the second page fits in sector 2. you could parallelize the execution of saving those 2 pages with the sparse file system support. You simply dispatch it asynchronously with correct hardware aligned memory, such as the only thing basically the NVMe SSD controller has to do is do a mem copy to a particular region on every NVMe SSD device. And so, there's a lot of, and so then when we rip the devices, when we rip the IOs, we can rip them in a totally unspecified order, semantics preserving. And so here you can say it's kind of like scatter gather. We send 4 pages, and then we'll rip them all at the same time at some point in the future. Let's see. There are a lot of other like low latency tricks. I do want to get into a demo. I know we're about 30 minutes in here. Let's talk about the thread per core on the Kafka partitioning model. I think this is fundamentally the crux and the thing that will tie all of these ideas together for people. I'm happy to talk about Raft and some of the optimizations that we've done there as a way of scaling Raft to hundreds of thousands of partitions on a particular machine. But for the purpose of this talk, given the time constraints that we have, let's walk through how does actually a Kafka layer work in a thread per core architecture, which is it's totally different. And I think general enough that you should be able to use this in your application if you choose to use a thread per core architecture. So one is that we tune the Linux kernel, and so we probe the hardware, and we say, this all happens, by the way, in like 100 milliseconds. We probe the Linux kernel and say, hey, that's your queue, that's your network interface card, that's your NIC that connects basically the wire connecting into your computer. Does it support multi-queue networking? And if it does, what we do is every core will actually poll for network events. We do the same thing on the NVMe SSD device. We instruct the Linux kernel to say, hey, on the particular core that dispatch the IO to the NVMe SSD device, only let that core reap the events, right? So reduce some of the locking mechanics or relax some of the locking mechanics. And two, don't interrupt the core, right? Because interruption causes jitter in your latency. And so what we do is we have a single thread. And so the single thread will rip the network, will encode it. At some point in the future, there's a scheduling priority set. It will rip the events from the kernel on the start side. And so everything is driven through a single loop. And so the loop here that you're seeing is that we rip a network request from the RPC layer, right? And so it's just a TCP translation. And so now we read the Kafka API, and then we translate it into our internal memory representation, and then it's our own storage engine. And just so that I think this is the fundamental disconnect with the majority of people that haven't taken a look, in part because we're a young company and we're just telling the world what the storage engine is we're a fundamentally new storage engine that has a Kafka API translation. So if you think of Redpanda that way, is actually a much easier way to understand the design choices that we've made. We intend to be 100% compatible. And so the idea is you take a Kafka API code base, and we have some customers like Zenly from Snap is using it, and some other Fortune 1000 people running it. We have oil and gas, IoT, etc. So you take an existing application, you point it at Redpanda, and it should just work. And if it doesn't work, it's our bug. In the request flow, the TCP connection gets translated at the RPC layer. And the thing to highlight here is at the bottom, you see this network of n squared number of queues. And so every core has an outgoing mailbox for every other core. So, and then there is a poll that will rip the events from other cores if it has nothing to do. And there's a schedule for that. But the fundamental difference here between that and the upstream implementation is that we don't have global data structures. And so when you don't have a global data structure, you have to do two things. One, you have to materialize a little bit of metadata on every single core so that you could look up information like, I got a Kafka request, but it doesn't make any sense because I don't have the access controls. Or I got a Kafka request, but I'm not the leader for this partition. Or I got a Kafka request and this topic doesn't exist. There's two ways, right? Imagine 32 simultaneous executions of a program and it lands on core 16, but only core 1 has the source of truth. So your choices are you either jump to core 1 that has the source of truth, or you materialize the copy. And so what we do is this hybrid, which is when we jump to the remote core, right? So if core 16 doesn't have the information, it'll jump to core 1 and say, hey, give me this information because I need to go back to core 16 to give back the TCP connection the information that it's asking for. But on the way back, we attach a bunch of metadata. And so what it allows us to do is to amortize the cost of metadata lookup. And so at all times, once the system is at a steady state, the cores have only a small view, but it's only the view that they need, and it's materialized and invalidated asynchronously. So it all plays well with the Kafka modeling technique. So what I'm trying to get at here, it is a fundamentally new storage engine with a thread per core architecture that has a bunch of metadata caching. And what it allows us to do is actually play with the hardware a lot, right? And so because we are adapting to the way hardware works, one of the last technique that we wrote is this two-phase trigger cause write request splitting. It's kind of this mouthful thing. But the idea is that the job of the storage engine writer is to saturate the NVMe SSD device, fundamental, like full stop. Like when we go and we sell on customers the Redpanda, we're like, we don't even compare Redpanda against anything. We actually compare Redpanda against the hardware. And so you go on your NVMe SSD device and they ask you run FIO, right? So this tool written by James Aksobi, who used to be a kernel developer for the last 30 years, now works at Facebook, who wrote IO Uring. He has a tool that tests the IO capacities of the NVMe SSD device, and it said just test it, right? This is how the Linux kernel, by the way, tests storage devices. And so if you're testing a new appliance, you use FIO. That's how we actually fundamentally want our customers to understand what Redpanda could do for them. We should be able to saturate hardware on the network and on the storage device. So on the network, you use iPerf, and on the storage, you use FIO. And then we're still like, we should be able to saturate whichever one is your slowest link. And so there's a lot of freedom to that. Let's see, timekeeping is 37. I want to jump into the demo. Two things. Feel free to ask me a question on Twitter. My handle is @emaxerno is on this. There's also a Slack if you want to chat. This that we keep is all community driven, really there. The code is available on GitHub. I'll stop here before I jump into the demo for a couple of minutes of questions, and then I'll jump into the demo. Let's see. Did I lose everyone?
No, we hear you.
Okay, awesome. Let's see, I'm happy. Let me make sure I'm going to my terminal.
Okay, maybe one question before we start the live demo.
Sure.
So can it work on distributed nodes some way like GlusterFS does?
Yeah, so Redpanda is fully distributed. We actually just added a new feature and we made it part of the open source. I thought about putting it in the enterprise, and then I wanted to add it to the open source, which is automatically rebalances a cluster. So the only operations from someone running a cluster should be adding a node or removing a node. Fundamentally, the system, there's this anti-entropy mechanism that we added. We haven't blogged about it. We're going to write about it next week, but it's already released. And so it works obviously in a distributed fashion, and that's how we run our cloud. So we run our cloud for some Fortune 1000 companies, and obviously they care about HA. So most people will start with like a 3-node cluster. They'll upgrade to 5-node and 7 nodes and 11 nodes and so on. But I think by and large, we can handle most people's traffic with a 3-node cluster. Does that help?
Yes, brilliant. That's what I needed to know. Thank you.
Awesome. Let's see, there's one more question and then I'll jump into the demo. Redpanda is same as Pulsar, more distributed version, messaging service. Exactly. So let me give you other competitors to us. So you have RabbitMQ, you have Pulsar, obviously you have Apache Kafka. And so there's a fundamental different philosophy in that Redpanda is a single binary. It's one C++ binary, full stop. There's nothing else. So it's super easy to use, right? Like you take one binary, you copy it on 3 computers, and you're done. Full stop. There's no other service. And so let me give you the alternate fault domains with existing systems. So let's take Kafka, and then I'll expand on Pulsar. So Kafka, you have the Kafka broker, obviously. You have Zookeeper. I understand there's skip 500. So Zookeeper is going to be replaced by a new set of services, 2 fault domains still, called the Quorum service. So 2 fault domains. Often people will add an schema registry and an HTTP proxy, right? So often people have about 4 distributed systems to do streaming. Pulsar added one more service, which is the front-end servers, right? And Redpanda embeds all of that in a single binary. And so what it means is we have an HTTP layer that translates an HTTP request into the Kafka format, right? It's a very small layer. It's in C++. It's super fast. It's like microseconds. But it lets people from non-native Kafka clients connect to Redpanda. To give you a sense, it took Travis Bichel, who worked at Fastly for 2.5 years, on creating a Kafka compatible driver. It took him 2.5 years to build the Kafka compatible driver. So the Kafka protocol is fat and non-trivial on the client side. Everyone that has worked with Kafka will have that. Pulsar is the same, by the way. There was design in an era where it was like, intra-data center replication. So Redpanda embeds that. There's also a schema registry. This is all part of the BSL license, so you can all run it. And it's fully compatible with the Kafka API, right? So whether you want to use just the schema registry or the HTTP proxy or Redpanda, obviously we don't use Zookeeper. And so those are just the small things in my head, which is every enterprise developer needs when you're actually trying to productionize the streaming system. Anyways, I'll stop there for a second because that could go on forever. And I'll jump to the demo. Hopefully that works with everyone. Let's see, where is my terminal? Okay. Can you guys see my terminal okay? Might be too small for people.
Yeah, all good.
Okay, so the way you install, let's see. I already installed Redpanda, so you can, here. I was just actually installing this last time. Curl. So there's a single curl command. We'll run it here. And then it installs Redpanda, it understands that you run it on Ubuntu, version 20, blah, blah, blah. We already have the latest one, so it's not going to do anything. It's going to start it right now, but before it started, let me pause it. Stop Redpanda. So let me stop Redpanda for a second. So if you see on my screen, I have a 64 core computer, 120 gigs of RAM. I just got a fancy desktop recently. And we're going to run 1 million messages per second. Maybe we'll do 10 million messages or 100 million messages. It's a lot of fun to do millions of messages in such a short amount of time, but it's also anticlimactic because it happens so fast. So, okay. So the way you tune it in production, when I was saying, hey, we actually probed the hardware, you say RPK tune prod. Tune all. Yeah. So right now we'll actually go and we'll probe the hardware. And so things that we've done is that we increase the number of AIO events. We tuned the disk IRQ. We disabled the Linux kernel IO scheduler. And so this is the block scheduler. So we prevent the block scheduler from merging IOs because we align it with the hardware. We tell the Linux scheduler to just do first in, first out, right? So FIFO dispatch to the NVMe SSD device. If you're running on GCP, we also disable the write-through cache. We make sure that your FS stream is enabled for your NVMe SSD device. We make sure that your network it's adaptive, whether it's single queue dispatch, multi-queue, blah, blah, blah. We make sure that swapping is available, etc. The point is, as a user, there's one command to make sure that it runs in production. And this is all in the open source version, we are the storage experts. So we will tune your hardware. The claim is you cannot do better than we can, us being the storage experts. if you can, then we have a bug in RPK, and we'll try to embed that knowledge to make sure that everyone else in the world doesn't have to follow 30,000 steps with getting. Okay. Now that you started, you just say, you just started here and you say systemctl start Redpanda. So I'll take a second here to get started. As you can see, you'll see a little bit of CPU utilization. And now we ship a tool, just like, Kafka has a bunch of tools that are like bash scripts. We ship the single binary called RPK. It's written in Go. It's really nice. It works with any Kafka compatible, right? So you can actually use RPK against upstream Kafka or Ivan or Confluent Cloud or actually Amazon MSK. Obviously, we just ship it. So it just picks the Kafka API. We added a couple of other tools that are specific to Redpanda, but the majority of commands that I'll type here are Kafka compatible. So you say RPK, RPK topic list, there's no topic. You can say RPK cluster info, I think. It says, hey, there's one cluster, it's localhost, there's no partitions. So let's create a topic here. Let me go back and make sure I'm creating it the right way. So we're gonna create a topic with 64 partitions. And that's it. And so if I say RPK topic list, there are 64 partitions with one replica. It's called DataOps Poland. And then what we're going to do is we're going to launch a workload. And so let me walk through here real quick. And so I compile librd Kafka, right? So here, git rem. So as you can see, is Eden Hill librd Kafka that git. I didn't do anything. I just downloaded the entire Kafka tooling framework. So when I say Kafka API compatible, we internally even benchmark with upstream things. So what we're going to write here is we're going to do, let's see, 1, 2, 3, 1, 2, 3. We're going to write 1 million messages, 200,000 messages per second, or we'll try with x equals 1. Every message is going to be 1 kilobyte, 1,024 bytes. We're going to write to localhost. And so there it is. Now we just finished writing 1 million messages at the rate. So you can see the outgoing queue. Really, we couldn't even saturate the outgoing queue. So the first time, obviously, we wrote 200,000 messages and there's 190,000 backed, and then it sort of drained it super fast. Let's try to write 10 million messages, which I think will take just a little longer. This is with x equals all. So it's, sorry, this is with x equals liter. It means that we get to the same semantics as Kafka, right? And it'll take basically a few seconds, like 10 or 20 seconds. We'll run the same command with x equals 1, and then we'll also write gzip. So this actually enforces the entire API, and you can see the round trip is basically 1 millisecond. It's not registering it here. This is the Kafka API. It will register once we start doing in-memory writes. This computer happens to be super fast, and so it's actually, it's returning to the TCP connection, in less than a millisecond for the workload that we're doing. And as you can see, there's really no backlog on the outgoing queue for librd Kafka, right? And so, well, we'll stop it here. And let's write the original one, but let's do x equals all, right? So we're going to say x equals -1. We're going to write 1 million messages per second, just so I didn't think I'm running like some pre-recording session. And you should start to see a little bit of latency, right? And so what this is saying is this 100 milliseconds was because we had in-memory writes that we hadn't flushed. And so when you change the acknowledgement, we'll always choose the safer version. So here, let's run it again. We're going to run again another 1 million messages. So I think right now we've written something like 10, 11, 12, 13, 14 million messages. Let's write another 1 million messages right now. And this 60 millisecond latency is probably pretty stable, 60 to 70 milliseconds. So we're writing 200,000 messages per second. with 60 millisecond round trip time measured by librd Kafka. We can tune it here, but this is really jobs upstream. We can probably get this lower, maybe to like low double-digit milliseconds. We help some customers get to that. Let's see. The last one is, let's try the Z standard compression. Just like, why not? With Ax equals sol. So as you can see, compressed messages are a lot smaller. And so you can actually get the round trip time to be, so you're obviously trading CPU utilization for latency, right? So for network utilization. That is it. There's like, it's basically hands off. You can consume the messages. I don't know if, let's say RPK. This might crash my terminal because I don't know what librd Kafka. Say RPK topic consume. So there it is. It's just librd Kafka performance testing, blah, 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 blah. It's the timestamp. So you can use this with any. The last one is we give a little bit of interactivity for developers, and then I'll wrap up in 2 minutes and I'll open up for questions. So you can say RPK, let's hear now, RPK topic, create hello world. And then you can say RPK topic, produce hello world. DataOps Poland meetup. And then we want to consume that. So it's the RPK topic, consume hello world. And it says, DataOps Poland meetup, partition 0, size 22 bytes. This is the particular timestamp. And with that, that's a wrap. Questions? I also speak really fast, so you guys should ask questions. Or maybe everyone understood it.
No rush, no rush. We have plenty of time. But let's summarize. So there is no extra tools like Zookeeper in Kafka or Bookkeeper in Pulsar and all the stuff. So it's only the one single process in system, and it has been written in C, right?
Correct.
And what is story behind that C, not the fancy Scala, Java, or whatever, any other new way programming, but they all do like C?
Yeah, well, do you know what it is? I think I didn't know how to take advantage of the hardware so one, it really, I don't think no philosophy, no religion. I am agnostic. I think Rust is great. I wrote in Scala professionally for a few years. But the design for this was like, how do I drive hardware at saturation? And when you have that goal, it's very challenging to do that with other runtimes. And I was a competent C++ programmer, so just like, why not? Yeah, and I had been writing professionally in C++ for a really long time. So it's kind of a natural evolution. It worked out great. Some of the APIs that we're able to access are really challenging to do in other programming environments and are very easy to use in C++. So that's kind of the evolution of that. Does that answer your question? You're muted. Thomas, you're muted.
Yeah, you got me. So from my perspective, it's like you choose the best system calls that they give you the performance, and that's it, I would say. So simple, brilliant, I would say.
I got a few questions, if that's okay.
Yeah, go ahead, Ralph.
How do you deal with a faulty drive? Or well, do you have a resilience on a drive level?
Yeah, great question. So our replication is at the node level. So if you have a faulty drive, you could just turn up. There's a decommission. So that question is really deep. So let me answer it in 3 categories. First of all, there's an API to decommission the node. So if you have a node that is misbehaving, you can say curl post, and then you decommission that node. And Redpanda will automatically start an atomic configuration swap and start to move the data to another node if you want to decommission it. So that's first. 2, you could just turn it off, replace the hard drive, turn it back on, and it's a raft system, right? So it's a quorum. So The performance here, we wrote actually a super detailed blog post on the difference between ISR, which is a synchronous protocol, over Raft, which is a quorum-based protocol. And the takeaway is that Raft works in the best of majority, and ISR works in the worst of the nodes, right? So an ISR by design is the latency and performance that you get is that of the worst performing node for that particular partition. Raft as a quorum system operates in the best of majority. So with that said, you can decommission a node. The quorum system is a lot more resilient to gray failures. 3, you could just remove the node, change the hard drives, plug it back in, and we'll reconcile it behind the scenes. And when it's back up, like, you know, no user involvement. I think that's basically, does that answer your question?
Well, yeah, but that opens up a few other questions.
Go for it.
Okay, what do you do on a networking level? What do you recommend? Ethernet or InfiniBand or anything faster than that?
Yeah. So most of our customers are running just plain, you know, I think 40 gigabit, yeah, 40 gigabit NICs, 10 gigabit NICs. I think most people on cheaper data centers, I think 10 gigabits is the norm. On anything modern is 40 to, I think whatever is the latest, like 80 or something like that on non-bonded NICs.
Well, 800, sorry, 400 is well, you could get 400 Ethernet.
Yeah, well, then you're shifting the problem to the NVMe SSD device, right? Like a single NVMe SSD device, non-rated, is about 1 gigabyte per second that you can push. So if you rate 0, it probably gets you to about 3 or 4 gigabytes per second realistic in practice. I know that the PCIe bus is spec for like 16 or 32 gigabytes, but in practice, you can only get 1 or 2 gigabytes per second. So that's 2. So you're just shifting the bottleneck to the NVMe SSD device. So if you rate 0, you're probably able to get maybe 3 gigabytes or 4 gigabytes per second per machine. And then you're saturating the device, right? Like you're just moving the saturation points. So 10 gigabits usually works out pretty well on a large cluster. 40 gigabits is really nice in that you get tighter latencies because you're always operating on like then what Redpanda plus the storage device can give you.
Okay. So how about if your lowest atom level is a single node? How do you deal with commit write across your nodes? Have you got like a master node that controls all the ins and out for every single work node?
So great. So that is actually a Kafka part of the Kafka protocol. So there's two answers to that. One, there is a single, every partition is its own RAF group, and there's no coordination between any other nodes. There's one exception, which is our internal controller log. And every node gets a copy of that log, but it's very low traffic. It's only like maybe a kilobyte of data, and it says like, hey, RAF created a topic with 10,024 partitions. That's the only real information that is exchanged there. Just kind of critical, but very small amount of data. Everything else operates in like, you know, segregated pods of nodes. So because it's a leader election, the Kafka protocol by design has to work on a stable leadership. So when I wrote this, initially I started with like Cass Paxos, and Dennis, who wrote the Cass Paxos paper, actually joined us. But we moved to a stable leadership protocol, which is Raft, because when your Kafka client connects to a cluster, it has to have a stable leadership. It could swap leaderships, is okay, but by stable, it means it doesn't jump around between nodes. It picks a node. Once the node is connected and it says this is the leader, then all of the transactions for that TCP connection happen through that node. Does that help?
Great. Yeah, thanks.
Great. We have 1 more minute. I do have a hard stop at 10 a.m. PT, but is there anything that I can answer for anyone? Any? Feel free to try it and join our Slack if this is interesting. If you crash it, I'll send you a sticker. It's engineering only sticker. We only send it to people that find good bugs. So definitely worth trying it. Yeah.